let's talk about the dot product. So as we talk about this, we're going to look at it from an algebraic point of view, or I kind of call it more a computational definition. Computational definition. And then we'll look at it from a geometric point of view, and the geometry of the dot product will give us some tools to apply for later on. And one of the tools that we're going to use is the idea that when you dot two vectors that happen to be perpendicular, you actually get 0. So we'll use that piece of information to find an equation of a plane. And we're going into 3 dimensions, remember. And then we'll also use, as other applications, we'll apply it to vectors being projected on one another and apply it to work. And for those people who have taken Physics 250, I think the idea of work with vectors should be familiar to you. And if you haven't taken 250, then we'll see how it works out. So here's the algebraic definition. I'll do it for 3 dimensions, and I'll also get to introduce, if you haven't already seen it, the idea that we have I, j, and k as standard normal vector. Actually, we didn't really talk much about I, j, k. So let me go back to this screen in a minute and squeeze in a set of notes here for the standard basis vectors. And it should have been in your reading already, but let me talk about it real quick. And we'll be talking a little bit about basis vectors, what they mean. But if you have taken linear algebra, we'll eventually take it. That's really the idea of a basis or a set of basis vectors. That's where it's really studied in great detail. But for now and for us, let's talk about the standard basis vector. The standard basis vectors are in 2 dimensions, or 2 vectors, 1, 0, and 0, 1. And the idea that they're standard basis, the idea that they're basis vectors means any other 2-dimensional vector that I write can be written as a scalar multiple and addition of these 2 vectors. So, in fact, they call this the I vector, and they sometimes call this the j vector. And in 2 dimensions, that's how it's going to be defined. And like I said, if we pick any vector, give me a random vector in 2 dimensions. Minus 4, 3. What we're saying here is that minus 4, 3, or any vector for that matter, can be written as a scalar multiple of the first vector, your I vector. Scalar multiple means we're going to scale this. I'll scale that in a minute. And a scalar multiple of the second vector. And the fact that they're labeled standard basis vector, they're standard because that number that's going to go in these blank spaces are exactly the numbers that are made up of the components. So what's the number that goes in the first blank? -4, right? So -4 times 1. And -4 times 0 in the y, there's no contributions in the y. And so +3 for the contribution in the y. So another way to rewrite this vector is -4, and 1, 0 is that vector we define to be I. And then 3, 0, 1 is that vector defined to be j. So that's an example of how to write your vectors in standard basis form. Okay? And that's what makes it nice, is because you're just looking at these numbers. to be those scalars. So in 3D, we have 3 components now. So we have I, we have J, and we have K. And that's what these vectors, how these vectors are defined. And when you have any random vector in 3 dimensions, you can write it as a linear combination of I, J, and K. And then that's your standard basis notation. All right? So when you see a vector 3i minus 2j plus 7k, it's understood that you are talking about the vector 3, negative 2, 7. By the way, if you started to do homework or labs on chapter 12 and they want a vector, you know that the vector notation is with that these special brackets, right? Oh, it does? Okay, great. So it apparently accepts parentheses, which is great because I want us to be flexible in writing a vector looking like a point or looking like a vector. Yeah?
So I tried putting it in as I and J, and I don't know if I need actually a vector sign or a hat sign, a caret. Or so they have to be bold. There's an actual button on it. Okay, that's why I kept getting it wrong.
Okay, so boldface. So their notation for vectors, you know, it's boldface if you don't have that arrow. So if we're dealing with computers, I think boldface is easier to write out rather than if you're handwriting it and you want to boldface something, that looks weird. All right, so that's a quick overview of standard normal or standard basis vectors. So when we see something written as U1, U2, U3 with IJKs, we know that those are just scalars, U1, U2, and U3, that makes up that vector as a point. And the definition of the dot product, I sometimes call it the working definition or the computational definition, but here I'm calling it the algebraic definition, it's the algebra of it, is that you just take each component and multiply them and then add your results. So that means, as an example, if you have U equals to, and I'll write it differently again, so 2, negative 3, 4, and then V, as an example, is 0, 1, negative 2, then the dot product computed. So we use this this dot or multiplication, but you make it a little bit darker to show that just to show that you're dotting it, and that should equal to 2 times 0 plus minus 3 times 1 plus 4 times negative 2. So minus 3 minus 8, negative 11. Okay. So what do we notice about our answer? It's a scalar, it's a number. So when you take the dot product of two vectors, you transform these two vectors into a scalar, just a number. And we did an example for 3 dimensions. We can also do an example in 2 dimensions that would work out exactly the same way. Yes? Dot product result is always a scalar. So when I ask you to dot something and you give me a vector, it's wrong. Okay? All right? And those are little things that are kind of important to me. And when I'm grading exams and you're supposed to do a dot product of something, and then I see a vector for your answer, I get a little annoyed. So. All right, so a dot product, a special kind of product that takes two vector and gives you a number. I don't know if this is a good time to talk about this, but the idea of a dot product well, I guess we have to extend the idea of vector. The idea of a vector is not necessarily points in Euclidean space, points in Cartesian coordinates and stuff, x, y, z. Sometimes we study, again, in linear algebra, we can study functions and call those functions like vectors. They act like vectors in certain ways, in some certain mathematical ways. So it turns out that you can take the dot product of two functions and get some sort of result if your dot product is well defined. And your dot product has certain properties and that we're not going to talk too much about, but it becomes really interesting to look into vectors that are not those arrows that we look at in space. So it works for any dimension. So like I said, it works for 2D also, but it works also for higher dimensions. So do you remember we had a 6-dimensional example of a vector? Your grade. So this is a snapshot of notes that we took on Thursday, and I wanted to just focus on the scale and somebody's grade. I thought we made up a grade for somebody. Did we do that?
It's 100.
So we'll call this vector P.
It was 160, 100, 75, 65.
This will be somebody's grade at the end, maybe not Pat's, but just saying. All right, so this is somebody's grade, and this is a scale that I had that we talked about, and I usually write my scale as a decimal, so I'll change that into a decimal. And for me to figure out the actual grade for this, I would simply take the dot product. Does that make sense?
Yes.
So the overall grade is going to be your vector P dotted with a scale vector. Let's put an arrow on top of that. And so whatever this turns out to be will be your final grade. And so that's 100 times 0.15 plus 60 times 0.15 plus 100 times 0.05 plus 75 times 0.35 plus 65 times 0.25 plus 100 times 0.05. So, anybody calculate this for me? 68.4. Professor Tong is going to teach Cal 3 next semester. Good luck. All right. So I have a bunch of these, and I just run them through a quick program to figure out the final scores, and this is what I get. All right. So this is simply a dot product. You just didn't want Patrick to pass, huh? All right, what is it again? Hey, Pat, what'd you get? Oh. So maybe it was a 68.4 after all, huh? All right, let's go with that.
Wow, you could not do well on the test and still do okay in class.
Yeah, it's all this little fluffy.
Fluffy. All this fluffy stuff.
It's the homework and what's this? Q. Oh, that's Q. Quizzes.
Oh yeah, see, you can not do long quizzes too.
So it's the homework and the labs, and the STEM speaker series. So, to stack up your grade, it'd be a good idea to just do 100% of all that other stuff. Just in case, you get a 75 and a 65 on your exams and stuff. It'd be nice if you were already, you've mounted up all the points as much as you can. So, do your homework. Or I could be like Professor Partland and kick people out for not doing homework. What class is he teaching? 270. I was talking to him earlier today. And he goes, "Yeah, I'm trying something new."
Was he laughing about it?
Professor locks the door at 8:10.
Oh yeah, he told me about that too. Yeah, I also started to do that lock the door business. Wow, tell me how it goes. Maybe I'll do that.
It's like mass protest. Right.
Well, what I was thinking was that not assigning any homework at all, not counting that. But you can see how important that is, right? You get 100% in the homework, it really stacks up your grade. So, anyways. All right, so you could count this as an application, but really this is a simple dot product of a couple of numbers, and we'll deal with applications in a few minutes. But first, let's take a look at the geometric interpretation of the dot product. And I guess I call it the geometric definition of the dot product. And the dot product happens to be the magnitude of each vector times the cosine of the angle between those two vectors. And when you have two vectors, either in 2 dimensions or 3 dimensions, or even in 6 dimensions, we can look for this idea of the angle between them. And when we're talking about an angle between two vectors in 2 or 3 dimensional space, we really just want to cover up to pi, 0 to 2 pi, because anything that goes past pi, you can look to measure that vector from the other side. So let's see if I can get some visuals here. So for an acute angle, that seems to make sense. For a supplementary angle, this idea is still making sense. And what we don't want is we don't want an angle that's bigger than pi. We're not going to look at that angle. So we want this angle, not this. When we're saying the angle between them, we're just taking a look at the smaller angle. Now let's take a look at the cosine function from 0 to pi and examine that just a little bit more, because there's some interesting facts that come out of this. Cosine starts at +1 when the angle is equal to 0, and it goes down to -1 when the angle is pi, and then we're going to ignore this other stuff over here. right? Because we only want this to go from 0 to pi. So a couple of interesting things are happening here. First, if we focus on the top part of the graph from 0 to pi over 2, we see that it's positive, right? Cosine theta is positive when theta is between 0 and pi over 2. Whoops. So if you have an acute angle between the two vectors, we know that you're going to get a positive dot product. On the other hand, cosine of theta is less than 0 when your angle is between pi over 2 and pi. So there you have an example of a dot product that's negative. If the angle is obtuse, then you have a negative dot product. So it goes from continuously, goes from positive to negative, which means at some point you have to cross 0. So that also is a special point for us. Cosine of theta is equal to 0 when theta is pi over 2. If you translate that to the idea of the dot product, that means if you have the angle between two vectors as being perpendicular, 90 degrees, pi over 2, then the cosine is going to be 0, and it doesn't matter what the lengths are of those angles. When you multiply anything by 0, you get 0. So the dot product is equal to 0. So that is one of our biggest keys, biggest helpers for finding out whether two angles are, or not two angles, but the angle between two lines or two vectors is perpendicular, is that if we take the dot product of those two things and we get 0, that means they must be perpendicular. All right? Make sense?
So on the, if you do it the other side, where you actually have a set of numbers for I, J, and K, each number would correspond with a 0 when you do the dot product at 90 degrees. Is that right?
They won't necessarily correspond to 0. When you add them up, they become 0.
Oh, okay, yeah.
Yeah, so they don't necessarily correspond to each other. All right? And if you take this equation and examine all the different scenarios when the angle between them is 0, when the angle between them is pi, when the angle between them is pi over 2, you'll see interesting things happening. I'll let you explore that. Okay. Any questions? All right. So let's actually oh, there's some more properties here. Oh, let's write these properties down, I guess. So this is when they start using Greek letters for scalars. They use alpha. In this case, they use lambda. So for any two vectors, it turns out that the dot product is commutative. When you switch the order of the dot, it still will give you the same answer. The dot product is distributive down below, or that particular product with the adding two vectors is distributive. And then this one is interesting. You have a scalar times a dot of two numbers is equal to the scalar times one of the vectors dotted with the two numbers, or the other vector scaled dotted with the other vector. Okay? So that's weird. How come they don't have this property here? Shouldn't this be one of the properties in the list? Yes? No? Should we add it in our list? What's wrong? Aaron just gave me this funny face. What? Because I wrote it down? I typed the other ones. How can you trust that? There's something fundamentally wrong with this. What is wrong with this? What? Redotting is scalar. Yep. Good job, Daniel. Dot product, what's the result? Scalar. So this is going to be a scalar times a vector. Well, times, I mean, we put dot here, so the whole idea of this doesn't make sense anymore. And likewise over here, this is another scalar when you dot it, and so there's absolutely no guarantee that this is going to be true. So this property doesn't make sense because of the fact that when you dot two vectors, you're supposed to get a scalar. All right? So we have to be really selective with our properties that we use. We have to know when something ends up to be a scalar, when something ends up to be a vector, etc. And when we introduce the other product, then there's going to be more properties where it's really going to be important that we look at the result and anticipate if the result's going to be a scalar or a vector. Okay, let's see if we can jump into some applications now. We're going to look at an application with geometry. Actually, before I copy all this stuff down, let's see if we can generate this idea of a plane. Generate this idea of a plane. Okay. Let's say you're in space and you have a point in space floating around. And then let's say you have a vector that's also in space floating around. Now that vector has a magnitude and a direction. I don't really care about the magnitude, but I do care about the direction. So it doesn't matter where it is, we have a specific direction. What if I want to have that vector perpendicular to a plane that I'm looking for? Does that idea make sense? So I have a vector. I want to come up with a plane. Whoa. Make it perpendicular. That what? Yeah. That's the same picture. Oh, I know what. Bam, perpendicular. All right. So I have my point and I have my vector, and then I want to figure out what this plane is, right? And the way we've been describing sets of points, like when we're dealing with conic sections, we say, okay, a parabola is all the points that's equidistant from a focus to the directrix and stuff like that, and then the hyperbola, a parabola, or the ellipse, they all have some sort of equidistant thing being described. And so we can kind of do the same thing. Let me come up with a, wait, this is a point that we know. Let's call this point ABC. No. X naught, Y naught, Z naught. So we know this. we have a vector, let's call it n, or let's call it capital A, capital B, capital C, and we know this also. So we know the point and we know the perpendicular vector. I call it n, by the way, because sometimes we say normal for perpendicular, so this is your normal vector that we know. Now, I want to describe all the other points x, y, z that are on this plane. Okay? So this is kind of a slightly confusing mathematical concept, I think, that this point x, y, z can be anywhere on the plane as long as it's on the plane. Then I have my point x, y, z. Right? Just like the points on the parabola, they're called x, y on the parabola, and they're just x, y. As long as they're on the parabola, then we know that they're on the parabola. Yeah?
Don't we need to know what the plane, is the plane an xy plane or a yz plane or whatever?
Well, that's the thing, is that it doesn't have to be. Because if this normal vector is not going straight up or, going along.
The vector's going like this. Here's the plane, and the vector's coming out of it like that?
Mm-hmm. We good so far? All right. So whether we're good or not, we're going. So I have 2 points. I'm kind of interested in the vector connecting those 2 points. Can you tell me what this vector is connecting these 2 points? You remember that? Right? You just head minus tail subtract. Thanks, Jesus. So it's x minus x naught for the x component, y minus y naught for the y component, and z minus z naught for the z component. And remember, it doesn't matter where this was as long as it's on the plane. Right? Now, as long as this is on the plane, speaking of as long as it's on the plane, as long as this is on the plane, what can you tell about that vector compared to the normal vector? They're perpendicular, right? They have to be perpendicular. So let me add on a little symbol that says those 2 vectors are supposed to be perpendicular. It really doesn't look perpendicular, but we'll go with it, yeah. So if those 2 vectors are perpendicular, what does that mean?
That means the dot product is 0.
That means the dot product is 0. The dot product of which 2 vectors again?
Green and the red.
The green and the red. So the red is ABC. And we dot that with x minus x naught, y minus y naught, and z minus z naught. And because that point is on the plane, this vector has to be also on the plane. And because this vector is on the plane, it has to be perpendicular to the normal vector. And because that's true, the dot product has to be equal to 0. It's like a domino effect, right? All these things start happening. What? Yeah, domino. Domino? Yeah. That's a good analogy. Whatever. So let's take the dot product. What's the dot product look like? It's A, x minus x naught, plus B, y minus y naught, plus C, z minus z naught is equal to 0. So now I started off with 2 vectors. Well, I start off with another bunch of things at the beginning of the domino. And now I'm here, and I took a dot product of 2 vectors, and I get a scalar. And so this is a scalar that I have. And so now we're looking at a scalar function or scalar representation or a relationship between x, y, and z. So you can leave it like this. This looks like an equation of a plane. But usually people do a couple of other things to, massage it a little bit, to get the kinks out. If you multiply everything out, and do one more thing, and the x naught, y naught, and z naught are known, is a known point, and x, y, z is an arbitrary point. And usually, if you leave the arbitrary points to x, y, ax plus by is equal to c, like that standard form of a line, equation of a line. Well, we can have the same sort of business here. And if I bring the ax naught and the bx by naught and the cz naught on the other side, they become positive. Not like that matters, because if this is just a number, we'll just call it d. So we have a nicer, more compact looking equation of a plane that kind of looks like the equation of a line that we learned in 3rd grade. Pretty cool, huh? What did we have to know in the beginning? What 2 pieces of information do we have to know in the beginning? Perpendicular. Whoa, that's an eraser. I meant to get the highlighter. And one of the points on the plane. So if you know a point and a normal vector, then you can find the equation of the plane. That's like knowing the point and the slope in 2 dimensions, right? If you knew the point and the slope of a line, find the equation of a line using whatever it is you use to find the equation of a line. If you have a point and a normal vector, you can find an equation of the plane. Suppose you want an example. So let's do an example. Give me a point. Give me a normal vector. What? We're all positive here, huh?
Are we just taking the assumption that
Yeah, this is a normal vector. You just happen to know the normal vector.
Okay.
Just happen to know it. There'll be times where you're going to happen to know the normal vector. I'm going to ask for the equation of line. So, all right. Well, A, B, C, AX, BY, CZ. I got like 75% of my equation already. This is my A, my B, and my C. That's the normal vector, right? And you have to know where A, B, C comes from. So your answer is going to look like 1x plus 3y plus 5z equals. Now we're going to struggle a little bit with D, but it's not really a struggle. It's easy computation. According to our formula that we came up with, AX naught B, AX naught BY naught CZ naught. Does that look like something? It looks like a dot product. It looks like a dot product. Whoa. Really? And it's a scalar, right? It looks like a dot product. What are we dotting?
The point and the vector.
Kind of weird. We're dotting the known point and the normal vector. So instead of memorizing this formula, well, what if you just remember that if you take the dot product of the point and the vector, let's call this point P as a vector in standard position. Your D is really just the dot product of the point and the normal vector. And that's easy enough to do. That would be 2 plus 27 plus 35, big number. It's too big for me. 64. I had 54, but done. This is a piece of cake. All right. So now you know how to get the equation of a plane, right? And we will be dealing a lot with planes. All right. Another application? Sure. Let's do another application. Equation of a plane, blah, blah, blah. Let's just skip over that. Vector projection. Now, there's two types of projections that we're going to be dealing with. One of them is a scalar projection. The other one is called a vector projection. So the scalar projection looks like this. And we denote it with a COMP as in component projection. And the picture that goes here is this is a component projection of V onto W. So the W is a subscript of a component, and that means that's what you're going to project this on. And the idea behind a projection is that if you shine a flashlight, does that look like a flashlight? It's a flashlight. You guys are going to have to do a flashlight. If you shine a flashlight directly on this vector that's perpendicular to the vector you're projecting onto W, then the shadow that this makes is a length called the component projection. Okay? The dot product of the two vectors over the magnitude of the not longer, but where it's being projected onto. Okay? So that's the component projection. And it gives you a scalar. And I said length here. I want to put the length in quotes because another picture might look something like this, where you project it onto W, but it turns out to be on the other side. So you'll have an obtuse angle that would give you a negative value. Okay? No big deal. Just negative.
That's also why 90 degrees, you're not shining anything, right?
And so in 90 degrees, there's no shadow. The length is 0. You're at a dot. All right? Now, this is formally called a scalar projection. If there's a scalar projection, then there probably is a vector projection. Well, no. There is a vector projection. Where the result that we have is actually a vector. So in this vector projection case, we denote this as proj, as in projection of V onto W. Notice how I said that in the order of V first and then onto W. W is the subscript. And for this particular projection now, instead of just the component, instead of just finding the length, I'm actually interested not just in the length, but in the actual vector. I want this vector going in the direction of W, but I only want it as long as V's shadow onto W. What do you think the formula of this is going to be? It's the same. Well, this is a scalar. Look, if you look at this carefully, you have the dot product up on top, which results in a scalar, and the magnitude, which results in a scalar. And this is a scalar for your result for the component projection. Now, the vector projection, I essentially want it to have this length, but in the direction of W. Think about that. Times the unit vector in that direction. So if we take this component, this is the length, V dot W over the magnitude of W. So this is the length. This is how much you want to scale this by. And we had an example where we wanted to scale to 5, and then we had to find the unit vector first. So what's the unit vector that I'm going to multiply this by? W? Well, we don't know if that's a unit vector. How do you make it into a unit vector? Divided by the magnitude. So this is not a dot, but a times. This is a scalar. Oh, I just made the dot bigger. What if I just put a parentheses over one of them? So we have a scalar times a vector, but this vector has another scalar that you're dividing by. So why don't we scoot that over onto this scalar? And so what's our revised formula going to look like? So this is your formula for projection. It's V dot W divided by whatever you're projecting it onto, the magnitude squared, times the vector W. Okay? All right, well, there's one very important application that we didn't get to today, and we'll talk about that some other time next week. I think that's it. Is this okay up to here? It looks okay until you do homework, right? Good luck in your homework.